Hello and welcome to Algebra 2 Lesson 61. In this video, we're going to learn about complex numbers. So the purpose of this lesson is to deal with the situation where you have to take the square root of some negative value. And this comes up immediately in the next lesson when we start working with quadratic equations again. A lot of you will recall back in Algebra 1, we ended our course by learning how to solve quadratic equations using the quadratic formula. But it doesn't matter what method you're using, if you're required to take the square root of a negative value, until you have the lesson where you learn about complex numbers, you basically have to just stop the problem and say, hey, there's no real solution. So let's talk a little bit more about why there's no real solution. Previously, we learned that when we square a number, the result is non-negative. So we all know if we take something like -1 and we square it, we're going to end up with 1, right? Positive 1. If we took -4 and squared it, we're going to end up with positive 16. So on and so forth. The only thing you can have as a result of squaring something in the real number system is either 0 or some positive value. But you'll never get a negative value from squaring, again, in the real number system. Now, here's an example of something where we run into this problem. If you see x squared plus 1 equals 0, let's just start by subtracting 1 away from each side of the equation. So that would cancel, and we would have x squared is equal to -1. Now, what value can you think of that you could plug in for x that when it's squared would produce a -1? You can't, right? Again, if I have a real number and I square it, the result is either going to be 0 or it's going to be positive. So using real numbers, I cannot get a solution. So up to this point, we just stop and say there's no real solution. But in mathematics, we always find ways around things, okay? So we're going to introduce today the imaginary unit known as I. And the definition I'm going to give you here is that I squared is equal to -1. Now, if we were to manipulate this, let's say we have this I squared, and this equals -1. If we take the square root of this side and the square root of this side, what's going to happen is this would cancel with this, and we'll just have I, and this is equal to the square root of -1. So we can now use this property, this definition, to proceed when we want to take the square root of a negative value. So let's look at an example of this. Let's say you see the square root of -9. And again, a lot of students get confused because they're like, oh, I already know how to do that. That's equal to -3. No, it's not, okay? Don't get confused between the negative square root of 9 and the square root of -9. These are different. This is just the negative of the square root of 9. This is just -3. With this guy right here, I'm taking the square root of a negative number. This has no real solution. But again, if we define I to be equal to the square root of -1, then we can use a little trick. We could say this is equal to the square root of -1 times the square root of 9. Let me erase this real quick. We can replace this right here with I, because I is defined to be the square root of -1. So I'm going to write that out in front. I'm going to put I out in front times the square root of 9. And the square root of 9 is just 3. So this is 3 times I, or 3I. That's all we're doing. We've just found a workaround for this problem of taking the square root of a negative number. Now, some people will write this as the square root of 9 times I like that. The reason that I don't do that, and the reason that most textbooks don't do that, is you don't want to make a mistake. Maybe this is extended a little too far, and you think the I is under the square root symbol. You don't want to run into that. You don't want to make that mistake. So to make it crystal clear that I is multiplying the square root of 9, we usually stick it out in front. All right, let's just look at a few practice problems, just get our feet wet here. So let's suppose you see the square root of -10. So what we're going to do is we're going to break this up into the square root of -1 times the square root of 10. And again, we know the square root of -1 by definition is I. So just replace it with I and then times the square root of 10. Square root of 10, you can't do anything else with that. 10 is 2 times 5. No perfect squares there, so we just leave this as I times the square root of 10. Then we have the square root of negative 20. If you see the negative, you can just go ahead and replace it with an I out in front times what would be left would be the square root of 20. Okay, you don't need to go through this every time. But just for the sake of completeness, let's just keep doing it. So we'll put the square root of negative 1 times the square root of 20. So again, this is by definition I times the square root of 20 is what? It's 4 times 5. 4 is a perfect square. And times the square root of 5. We know the square root of 4 is 2. So if we completely simplify this, we'll have 2i, because again, the square root of 4 is 2. 2 times I is 2i. Then times the square root of 5. For the next one, we have the square root of negative 15. Again, the shortcut is just to take this, say, hey, this is I, and then times the square root of 15, and you'd be done. But the long way, again, if you just want to realize what's going on here, this is the square root of negative 1 times the square root of 15. The square root of negative 1 is by definition I, then times the square root of 15. Then what about the square root of negative 3? Again, this is the square root of negative 1 times the square root of 3. This is I by definition, so this is I times the square root of 3. All right, now we have the negative of the square root of negative 50. So be very, very careful here. You have a negative out in front, so let's leave that out in front. Then I'm going to break this up into the square root of negative 1 times the square root of 50 we know is 25 times 2. 25 is a perfect square, so let's break that up. We'll put 25 under our square root symbol, then times the square root of 2. And we know this has a value of 5, so let's just go ahead and replace it. We know this is basically I. So you would have negative I times 5, or negative 5i, and then times the square root of 2. All right, so now let's talk about some kind of immediate applications of this. We want to make sure that you're crystal clear on the product rule for radicals. So when working with multiplication and division, we must change the form first. So here's what I mean by that. Once people know that they're allowed to take the square root of a negative number, the first thing you start seeing on your tests, when you give this out, you'll see somebody go, okay, square root of negative 2 times square root of negative 18, that's going to be the square root of negative 2 times negative 18. This is the square root of 36, which equals 6. No, that is wrong. Okay, this is wrong. Okay. The correct way to do this problem is to break it up section by section. This right here, again, becomes I. This right here becomes I. So if we break it up and say we have I times the square root of 2 multiplied by I times the square root of 18, what do we get? Well, I times I by definition is I squared, which is negative 1. So let's just put I squared for now. Then times, you'll have the square root of what? Let's break this down. You'll have 2 times, 18 is 2 times 3 times 3. So essentially we know that 1 2 would come out and 1 3 would come out. 2 times 3 is 6. So what you'd end up with is 6 times I squared. And I squared, again, by definition, is negative 1. So this would be 6 times negative 1, which equals negative 6. Now, again, if you did this the wrong way, your sign would be incorrect. If you did this like this, you'd end up with positive 6. That's, again, not correct. This is the correct way to do it. And then this is incorrect. Okay, this is wrong. So you've got to make sure that you change the form first. Don't just go through and apply the product rule for radicals as you know it, because that's not going to work when you're taking the square root of a negative. The same thing is going to apply when we get to a division problem as well. All right, let's take a look at some examples. So we have the square root of negative 8 times the square root of negative 4 times the square root of 2. So I can't just say, hey, I have the square root of negative 8 times negative 4 times 2. It wouldn't work out that way. What I've got to do is change the form first before I do my multiplication. So we all know if we see a negative, we can just replace that with I. Okay, we can just replace that with I. So what we do is we say we have I times the square root of 8 would be what? It would be the square root of 4 times the square root of 2. Then you'd have times, you've got I times the square root of 4 then times you've got the square root of 2. So what is this equal to? Well, we know that this right here has a value of 2. We know this right here has a value of 2. And we know if we took the square root of 2 and multiplied it by the square root of 2, those two together would have a value of 2. So what we're going to have is I times I, or I squared, then times 2 times 2 times 2, or 8. So this ends up being 8 times I squared. I squared by definition is -1. So 8 times -1, which is -8. And again, this is the correct way to do it. If I had gone through and just multiplied and said, hey, this is going to be the square root of -8 times -4 times 2, I would have had the square root of 64, which is +8, right? I would not have ended up with -8, so I would have gotten the wrong answer. All right, what about the square root of -5 times the square root of 8? So again, if I see this, I'll replace it with I. So this is I times the square root of 5 multiplied by, for the square root of 8, we'll put the square root of 4 times the square root of 2. So we'll end up with I out in front, times the square root of 4 is 2, so let's put 2I out in front actually, times the square root of 5 times square root of 2. Square root of 5 times square root of 2 would be the square root of 10. So this would be 2I times the square root of 10. All right, now let's take a look at a division problem. So we have the square root of -100 over the square root of -4. So again, I don't want to just go through and say, hey, this is the square root of -100 over -4. What we want to do, we want to go ahead and set this up as I times the square root of 100. Again, just taking that out and replacing with I, over I times the square root of 4. Just taking that out, replacing with I. So at this point, you do have I over I. Same thing over itself. It's still going to cancel. Okay, still going to cancel. So then you have the square root of 100, which is 10, over the square root of 4, which is 2. Then 10 over 2 is going to give you 5. Now what about the square root of 28 over the square root of -7? So for this guy right here, what are we going to see? The square root of 28, we'll write it as the square root of 4 times the square root of 7. Then for this guy right here, we have the square root of -7. So let's take this out. We'll have I times the square root of 7. So we know that this would cancel with this. And we know the square root of 4 is just 2. So this would be 2 over I. Now, a lot of people will just stop and say, hey, that's my answer. But remember, I has a definition of what? I is equal to the square root of -1. We do not allow radicals in the denominator. So don't report an answer with I in the denominator because you're reporting an answer with the square root of -1 in the denominator. So what you want to do, you want to rationalize. We want to rationalize the denominator. So 2 over I, we can just say we'll multiply by I over I. And what happens is I times I is I squared. Then you have 2 times I in the numerator. I squared has a definition of -1. So you get 2I over -1, or -2I as your answer. All right, so let's talk a little bit about something known as a complex number. So we're used to just the real number system. Now we're going beyond that. We're talking about the complex number system. So a complex number is formed using the imaginary unit I, along with our real numbers. So you'll generally see this in your textbook written just this way. They say let A and B be any two real numbers. And we'll see our complex number. So this is known as a complex number. And it's written as A, which is a real number, plus B, another real number, times I, the imaginary unit. So A is referred to as the real part. And then BI is referred to as the imaginary part. In some textbooks, you will see that only B is described as the imaginary part. Your textbook might say that. The textbook I'm using actually says that BI is the imaginary part. It's basically irrelevant. It's not something you want to argue over. You just need to understand the structure of this so that when we start working with complex numbers, we know, hey, this is how we can add or subtract them. And we're going to this part right now. So in order to add or subtract complex numbers, we use our commutative, associative, and distributive properties. So we kind of think about this the same way that we think about adding like terms. So if I have something like 8 plus 2x, and then I add 4 plus 7x, we all know what to do. We take 8 and 4 and add those together, that's 12. And we take 2x and 7x, we'd add those together, that's 9x. Very, very clear what to do. It's the same thing here, okay? So I have 8 plus 4. So let's group that together. 8 plus 4. And then we have 2i plus 7i. I can't combine 8 and 2i together, okay? That's not going to work. It's just like trying to add 8 and 2x. What we do here, just to make this completely clear, we add 8 and 4, that's 12. And then for this guy, 2i plus 7i would be 9i. To make that crystal clear, you could factor out the I, right? That's common to each one there. And so you have I times the quantity 2 plus 7. And so this would be 12 plus 2 plus 7 is 9 times that I there. So you end up with 12 plus 9i. So it's just like adding like terms. It's the same principle here. Now, when we see it like this, where we have A, the real part, plus BI, the imaginary part, this is known as standard form for a complex number. So when you write something, you want to write it that way. You don't want to put 9i plus 12. You want to put 12 plus 9i. All right, let's take a look at another one. We have negative 2 plus I minus the quantity 6 minus 12i. So we have negative 2, and then plus negative 2 plus I. This will, again, get distributed to each term. So you'll have minus 6, and then minus a negative 12i would be plus 12i. So negative 2 plus negative 2 is negative 4. And then negative 4 plus negative 6 is negative 10. And then we have I plus 12i, which is 13i. And again, we wrote this in standard form. This is A plus BI, your real part plus your imaginary part. Let's take a look at one more of these. We have 7 plus 4i plus negative 8 plus 8i plus 2 minus 2i. So again, if I just go through and say, okay, the real parts, 7 plus negative 8 is negative 1. Negative 1 plus 2 is positive 1. Then your imaginary parts, you've got 4i plus 8i minus 2i. So 4 plus 8 is 12. 12 minus 2 is 10. So this is plus 10i. And again, this matches the A plus BI. This is your standard form. All right, now let's talk about multiplying two complex numbers together. And we basically use the same methods we would use for polynomials. So if we had a single-term polynomial or a monomial multiplied by a two-term polynomial or a binomial, what would we do? We just use our distributive property. You'd have negative 2i times negative 5. That'd be positive 10i. And then you'd have negative 2i times negative 2i. That would be positive. 2 times 2 is 4. I times I is I squared. Now, I squared has a definition of negative 1. So this is 10i plus 4 times negative 1, which is basically 10i minus 4. Now, this is not in standard form. We want the real number first. So we're going to switch the order and say this is negative 4 plus 10i. All right, now we have something that looks like the product of two binomials. So for something like this, we can use FOIL. We have negative 2 plus 6i, that quantity, multiplied by the quantity 6 minus 3i. So if I look at the first terms, negative 2 times 6 would be negative 12. If we look at the outer terms, negative 2 times negative 3i would be positive 6i. If we look at the inner terms, 6i times 6 would be positive 36i. And then the last terms, 6i times negative 3i would be minus 18i squared. So we have 6i and 36i, that can be combined. So we'll have negative 12. Again, 6 plus 36 would be 42, so plus 42i. And then minus 18i squared. So we're not done. We have negative 12 plus 42i. Here's the big thing. I squared is negative 1. So this would be minus 18 times negative 1. So we know that negative 18 times negative 1 is positive 18. So essentially you'd have negative 12 plus 18 plus 42i. Negative 12 plus 18 is 6. So we end up with 6 plus 42i. Again, this is in standard form. You've got your real part plus your imaginary part. All right, so let's take a look at one more of these. And just like if I was multiplying 3 binomials together, I would multiply 2 of them first, find that product, then multiply the result by the third. So we have 3 plus 5i, that quantity, multiplied by the quantity negative 7 plus 5i, multiplied by the quantity 3 plus 7i. So let's start by multiplying these two together. And what's that going to give us? So for FOIL, 3 times negative 7 is negative 21. The outer 3 times 5i would be positive 15i. The inner 5i times negative 7 would be minus 35i. And then the last, 5i times 5i is 25i squared. Now we know I squared is negative 1. So let's just go ahead and write plus 25 times negative 1. And again, this is times this guy right here. We'll do that in a second. Let's just simplify first, and then we'll multiply by this. So this would be equal to what? You'd have negative 21. 25 times negative 1 is negative 25. So let's put minus 25. And then 15 minus 35 is negative 20. So minus 20i. So negative 21 minus 25 is negative 46. So let's erase this. And we're going to write negative 46, then minus 20i. And this will be multiplied by 3 plus 7i. So we can use FOIL again here. So negative 46 times 3 is going to give us negative 138. The outer, negative 46 times 7i, is negative 322i. The inner, negative 20i times 3, is going to give us negative 60i. And then the last, negative 20i times 7i, is going to be negative 140i squared. All right, now remember, I squared is negative 1. So let's just replace this with negative 1. And so what we'd have is negative 140 times negative 1, which is positive 140. So positive 140 plus negative 138 would give us 2. Then negative 322i minus 60i would be negative 382i. So as our answer in standard form, we have 2 minus 382i. All right, now let's talk about division. Now, when you work with division, you're going to need to think back to when you rationalized a binomial denominator. Okay, we did that in a previous lesson. So recall we talked about this thing known as conjugates. So we have a plus b and a minus b. Those are conjugates, right? If you multiply them together, you use FOIL, you end up with a squared minus b squared, right? The middle two terms will drop out. It's not going to be any different when you're working with complex numbers. So here you'll have a complex conjugate. So a plus bi times a minus bi, those two are complex conjugates, and the result is a real number. Now normally if you have a plus b multiplied by a minus b, you get a squared minus b squared. With this, a plus bi multiplied by a minus bi, you're going to end up with a squared plus b squared. This is a big source of confusion. Here the sign is negative, here it's positive. Why do you think that is? It's because of this I times I, which is I squared, which is a negative 1, which changes the sign. So if we went through and did this, a times a is a squared. The outer, a times negative bi is minus a bi. The inner, bi times a is positive a bi. And the last, bi times negative bi is minus b squared I squared. Now, we know already that this would cancel. So what do we have? We have a squared minus b squared. I squared is negative 1, so times negative 1. All that's going to do is change the sign. If you have a negative times a negative, you end up with a positive. So this gives me a squared plus b squared. Okay, so that's where the difference in the sign comes in. All right, so the quotient of two complex numbers is a complex number. If we start out with something simple like 7 over 3i, we already talked about earlier the fact that I is what? It's the square root of negative 1. So we don't want to leave it like that. We want to multiply by I over I. Basically the same thing we've been doing to not have a radical in the denominator. This is going to give us 7I over 3I squared. Again, I squared is negative 1. So this is 7I over negative 3. And of course, you could also write this as negative 7I over 3. But these two answers are basically the same. All right, so what about something like 4 over 6I? Well, the first thing you would do is just reduce, right? They're each divisible by 2, so this would be 2 over 3I. And then again, because I represents the square root of negative 1, we just multiply by I over I. We'll end up with 2I over 3I squared. I squared is negative 1, so we'll end up with what? 2I over negative 3, or negative 2I over 3. All right, now let's take a look at one where we're going to need to multiply by the complex conjugate. So we have 2 plus 6I over 4 minus 3I. Again, I is the square root of negative 1. So really, we could write this as 2 plus 6 times the square root of negative 1 over 4 minus 3 times the square root of negative 1. We don't want radicals in the denominator, so we want to rationalize. All right, so if we want to do that, what would we do? Again, we worked with binomial denominators before, so we multiply both the numerator and denominator by the conjugate of the denominator. In this case, it's going to be no different. So the terms stay the same. 4 would be the same, and 3I would be the same. It's just that the sign is going to be different. Here it's a subtraction, so this is going to be addition. Now in the denominator, it's a breeze because we know the formula. It's a squared plus b squared. And again, the reason it's plus is because of that I squared being equal to negative 1, it's going to change the sign. So we'll go through this the quick way, and we'll go through it the long way. Let's do it the long way first. So if we do FOIL, the first 2 times 4 is 8. Then the outer 2 times 3I is plus 6I. The inner 6I times 4 is plus 24I. Then the last 6I times 3I would be plus 18I squared. Now we know this has a value of negative 1, so we can replace it. But let's just continue for now. In the denominator, again, the quick way is to realize that this follows a formula that's a squared, so 4 squared is 16, plus b squared. B in this case is 3. Forget about the odd. It's just a 3. So 3 squared is 9. So you'd have 16 plus 9, which is 25. Now I'm going to do this the long way, and you're going to see that this denominator down here is going to end up being 25 in the end. So 4 times 4 is 16. The outer, 4 times 3i is plus 12i. The inner, negative 3i times 4 is minus 12i. And the last, negative 3i times 3i would be minus 9i squared. Again, this I squared here has a value of negative 1. So keep that in mind. So we scroll down, get a little room going. If this I squared is negative 1, really I have 18 times negative 1, which is negative 18. Negative 18 plus 8 would be negative 10. So this is negative 10. Then plus 6i plus 24i is 30i. And this is over. You'd have 16 plus 12i minus 12i. This is going to cancel. And you basically have negative 9 times negative 1, because again, this is negative 1. Negative 9 times negative 1 is positive 9. So you've got 16 plus 9, which again is 25. So that's the long way to do it. The short way, again, a squared plus b squared. If you just remember that, you can calculate that denominator very quickly. Now, we're not done because we can simplify this further. Everything there is divisible by 5. So let's factor out a 5. We'd have negative 2 plus 6i inside the parentheses over, we'll write this as 5 times 5. We'll cancel a common factor of 5 between numerator and denominator, and we'll report our answer as negative 2 plus 6i over 5. Or if you wanted to, you could say this is negative 2/5 plus 6/5 times I. Either answer is acceptable. All right, for the next one, let's use our little shortcut for the denominator. We have negative 10 plus 7i over 1 plus 6i. Again, we'll multiply the numerator and denominator by the complex conjugate of the denominator. So this would be 1, instead of plus, it'll be minus, and then 6i over 1 minus 6i. To multiply the two numerators, let's use FOIL. So the first term's negative 10 times 1 would be negative 10. The outer, negative 10 times negative 6i would be positive 60i. The inner, 7i times 1 would be positive 7i. And then the last, 7i times negative 6i, would be minus 42i squared. Now again, this I squared has a value of negative 1, so keep that in mind. For the denominator, let's go ahead and just use our shortcut. We know that if we have a plus bi multiplied by a minus bi, this is equal to what? It's a squared, okay, the first value squared, plus b, okay, not the I, forget about the I, b squared. So following this, I would take 1, which represents a here, and square it. That's just 1. Then I would take 6, which represents b here. Forget about the I. That's already calculated for you with the sign. So 6, and then I would square it. That's 36. All right. And again, if you don't believe me on that, FOIL that out, and you'll see that you get the same thing. All right, so we have negative 42 times negative 1, which is 42. 42 minus 10, which is 32. So you'll have 32. Then plus 60i plus 7i is 67i. Then over 1 plus 36 is 37. So you'll end up with 32 plus 67i over 37. Now, nothing we can do to simplify that further. Another thing, again, if you wanted to, you could say this is 32 over 37 plus 67 over 37, and then times I. All right, so the last thing we want to talk about, and I know this lesson's kind of dragged on a little bit, we want to learn how to simplify powers of I. So this is something for sure you're going to see in this section. And basically it just cycles through these 4 values. So we start off with I to the first power, or just I. We know this is nothing more than the square root of negative 1, but we just write it as I for now. Then we see I squared. We know by definition this is negative 1. Then we have I cubed. Now what is I cubed? Using the rules for exponents, it's I squared times I to the first power. I squared is negative 1, and I to the first power is just I. I mean, you could rewrite it as a square root of negative 1, but for the purposes of what we're doing here, this is just going to be equal to negative, for the negative 1, times I. Let me erase all this, and we'll make it more compact. This is just negative I. And then lastly, we have I to the 4th power. So I to the 4th power is going to be I squared times I squared, which is negative 1 times negative 1, which is 1. Now, when you work with something that has an exponent, okay, that's larger than 4, let's say I saw something like I to the 18th power, and you get this on a test and you're like freaking out. What do I do? How do I simplify that? Well, think about 18. 18 is what? It's not divisible by 4. I mean, it's divisible by 3. It's divisible by 2. It's a lot of different things you can do here. But the quickest thing to do is think about, well, 18 is 2 away from a number that is divisible by 4. 16 is divisible by 4. So using my rules for exponents, I could say this is I to the 16th power times I squared. If you have I raised to a power that is divisible by 4, you can just say that, hey, this is equal to 1. It's just that quick. And the reason you can do that is, to kind of go through this, I could write this as I to the 4th power raised to the 4th power, right? 4 times 4 is 16. I've done nothing illegal. I to the 4th power by definition is 1, so this is nothing more than 1 to the 4th power, which is 1. So if you have I raised to a power that's divisible by 4, you can just replace it with 1. So this is basically 1 times I squared. Now, I've simplified this to the point where I can just look at my little chart here. I know I squared is negative 1, so this is 1 times negative 1, which is just negative 1. It's really that simple. If I looked at something really, really big, let's say I saw something like I to the power of, I don't know, let's say 603. Well, I would know that if I came across 600, that's divisible by 4. So I could write this as I to the power of 600 times I to the power of 3. So again, if you see I to a power that's divisible by 4, okay, 600 being divisible by 4, we can just mark it out and say this is 1. So this is 1 times I cubed. And I cubed, if I look at my little chart, is negative I. Okay, very, very simple. As another example, let's say that we looked at something like a negative exponent. Let's say negative, I don't know, let's say 9. So what do? We know with negative exponents we write 1 over I to the 9th power. So same rules apply here. We think about simplifying this. So 9 is what? If you think about 9, 1 less would be 8. 8's divisible by 4. So let's go ahead and do that. So we have 1 over, we have I to the 8th power times I. I to the 8th power, again, if 8 is divisible by 4, you can mark this out and just put 1. Because I can always just say this is I to the 4th power squared. I to the 4th power is 1. 1 squared is just 1. So anytime you get I raised to a power, and that power is divisible by 4, cross it out and just put 1. Okay, that's all you got to do. So what I'm left with is a 1 over I. Again, this represents the square root of negative 1. So we rationalize something like this. So times I over I, you would get I over, I times I is I squared, which is negative 1, which equals negative I. And again, this is a more complex problem that you might see. A lot of students will get this far. Okay, they'll get 1 over I, but they won't take the extra step of rationalizing the denominator to get this negative I as a result. So this right here, although it's not technically wrong, it's not how we report our answer, and so you will get marked off on the test for that. Okay, so you've got to make sure you report this and not just that. All right, let's take a look at another one. Let's say we had, I don't know, let's say I to the power of 57. Well, we know that 57 is divisible by 3. So would we want to do that, or would we want to do this? Let me ask you, what's better? Should I go I to the 56th power? 56 is divisible by 4 times I to the 1st power. We know this would be 1, so this is 1 times I, or just I. That was very quick. Let's say I said, okay, well, I know I cubed is negative I. Let's try it this way. Let's say this is I cubed raised to the power of 19. Is that going to get me anywhere? Really, all this is telling me is I have negative I raised to the 19th power. Does that get me where I want to go? No, it really doesn't, okay? I don't want to do that. I want to stick to things that are going to be very, very easy, because although I can figure this out, I can say this is negative 1 to the 19th power times I to the 19th power. Where does that really get me? Negative 1 to the 19th power is still negative 1. I to the 19th power is what? Well, I'm going to have to split this up. I could say it's I to the 16th power, or we can even do 18th power times I. Now, what I'm doing here, I to the 18th power, I could say this is negative 1 times I squared to the 9th power times, we'll have I. So what do we end up with? I squared is negative 1. Negative 1 to the 9th power is still negative 1. So you'd have negative 1 times negative 1 times I. Negative 1 times negative 1 is 1. 1 times I is I. Look at all that work I had to do to figure out what I figured out very quickly by just, and let me erase this real quick, and I'll go back to what I just did in case you forgot. By using the divisibility rules for 4, if I just said, okay, I to the 56 times I to the 1st, this is 1 times just I. So 1 times I gives me I. Look how quick that was versus what we just did. Okay, so don't make that mistake that a lot of students make. Try not to use these unless you need to. If it's a number for your exponent that's larger than 4, look for the next number down that's divisible by 4. So if it's 13, I'm looking to write this as I to the 12th power times I to the 1st power. This is 1, and you get 1 times I. If it's I to the 49th power, we know 48 is divisible by 4. So I to the 48th power times I to the 1st power. This is 1. 1 times I is just I.